So the algorithm to find a perfect hash function is first, we choose h1, uniformly from some universal class of hash functions. And we use n bins for that. So we build a hash table with n bins. And for each bucket, do we have notation for the buckets? I think we only had the size of the buckets. Let's just say for each bucket I, and this goes from 1 up to n. Now we only need to do something if there's some elements in there. If there's at least 2, then we draw a random hash function, hash2. And superscript I. From another universal class of hash functions. I mean, it could in principle be the same, but let's say it's some h prime, again, universal. And this we repeat, I should say, with xi squared. Sorry, xi is already the number. Xi squared bins. Repeat this until this hash function is perfect. And that's the part we already analyzed. That takes a constant number of repetitions in expectation. And that's all. So the output then is the hash function that we get from the inserting. So we output this as a function, or plus the hash tables. I guess we just built the hash table. But there's one more step here, in that we repeat the entire construction. I guess we can smuggle that into step 1. I don't have to move that. Until the number of collisions is not too big. And less or equal n should be good enough. So that's the algorithm we're proposing. Now we have to show 2 things: that it succeeds with good probability, or the number of repetitions is reasonable, otherwise it would run forever. And we have to show number of repetitions is small, and we have to show, not confuse that with the algorithm steps, and we have to show that the space usage isn't too big. That's the 2 things we need for this algorithm to be useful. And both is a relatively simple argument, so I'm trying to squeeze it into the part of the slide so we can still see the algorithm while we're doing it. For part A, we just use that the expected number of collisions we get by the same argument as before, because it's a pairwise independent function. Each of the pairs has probability 1 over n to collide, and so the expected number of collisions is just n minus 1 over 2, which means the probability that we get less than n collisions is going to be at least 1/2 by Markov. So we, in expectation, only need 2 repetitions for the topmost step, and for the part for the steps 2, that was in step 1. And in step 2, this is analysis from before. I'm just going to say C above, same result. Expected number of repetitions is 2. So over all of those repeated steps, we're going to get time proportional to what it takes to do one of these random samplings, and these are all fairly fast. So the overall expected time is going to be what? The time to draw the random functions is actually small. We have to compute the bins, and we have to find the functions here. So I guess it's going to be linear. Now for the second step, the space usage, if it succeeds the way we defined it, is upper bounded deterministically. The space we use is the space for the hash table cells and the hash tables, the hash functions. But that's, say, for the classes we looked at, that's 2 numbers per hash function. So we have linear, that's for the top level hash function, for the top level hash table, and all hash functions. And then we have a part that comes from the secondary hash tables. And because these all use xi squared bins, what we get is the sum over all the bins, xi squared. Now that seems potentially scary. All we know is that the number of collisions is bounded, but we already know how these relate. Because, okay, tiny side calculation here. We've established that from a single full bin, we get xi choose 2 collisions. So if we have xi squared, that's almost this. Right, this is xi squared over 2 minus xi over 2. And so we're going to rewrite this as the linear term from before. Might run out of space. We'll see. The space analysis runs out of space. Then we have the xi choose 2. And we have plus these guys. Now the second part here, that's summing up the sizes of the bins and divides by 2. So that's going to be less or equal n, or n half really. So that part goes into the theta of n bit. And this other term, well, every bin causes exactly that number of collisions. So what we're summing up here is all collisions. This is exactly our C. And C we assume was bounded by n as well. So in total, the overall space is theta n. And that just follows from the construction. The random part was just the time. So in a way, it's a Las Vegas algorithm with respect to how much space it uses. That's always fixed. And the running time, because of the repetition, is random. That's all on perfect hashing. With this combination of very simple tricks, you get some result that may at first seem relatively hard to even imagine that it's possible. But really, all of these we have achieved. The hash functions, we can pick our favorite pairwise independent hash functions from the random lines modulo prime. So these are easy to store as well. And we can construct a perfect hash function of using a linear number of overall space in linear time. So all of the requirements are fulfilled. And all that we needed is some clever random sampling and the two-level scheme.